Did amazing. And then I'm sorry. The question about the acceleration at 0 and the graph being in velocity.org.
Oh, yeah.
What?
You can tell he hasn't been down there.
No, Martinez not. Yeah, that's why I'm like, bro, you didn't comment saying that. There's no way we're doing the same thing. I don't understand this. I've never seen that. Like that's what's really good stuff, and I get it. Like you hear my teeth grinding because I know. I'm really talking about. Nice. I did my final scale. I'm in a definite number, and then the velocity and acceleration is 0. It's like, give me a it's only what? 1, 2, 3, 4, 5, 6, 7.
But is it the first one?
Okay, so we can turn to page 27.
Wait, I just never seen it.
One's the technical.
It's just all funny. Like, well, I'm taking it till we're able to. Now I don't want to. And now I'm the same thing.
You could take it.
Okay, so page 27. We haven't talked about this yet, so this is a very common type of AP exam multiple choice question that they like to give. So I want to make sure that we can do this, and we can also expect to see one of these on the test. So it says, let me read the problem here. It says finding constants to make a piecewise function continuous and differentiable. So continuous, what that means is no breaks, right? What does differentiable mean? Have we talked about that word yet? Okay, so differentiable means you're able to find the derivative at every point. A nice visual is that it's a smooth curve. Okay. So not only do we want the graphs, these is a piecewise function, so not only do we want them to connect at the same y value, so that's continuous, but we also want there to be a smooth transition where the slope at one endpoint is going to match the slope at the other endpoint, so that it won't be a sharp turn or a sharp corner. So we want to be able to, so right now A and B are constants. We don't know what A and B are. We're trying to find A and B so that the two graphs will nicely connect in a way where not only is it sharing the same y value, but also sharing the same slope at x equals 1. So there's two, because we have two expressions, and because we're looking for two different unknowns, constants, we have to use two different equations to help us solve for our two unknown values. So here's our strategy. Because the fact that they're continuous, what that means is they must share the same y value. At x equals 1, right? We want the graphs to connect at x equals 1. So what we can do is we can set the equations equal to each other, because we know that at x equals 1, they must agree, or they must match with the same y value. So ax plus 3 is equal to 3x squared plus x plus b, and this is going to be at x equals 1. So what I can do is I can replace every x with 1 and see what I have left. Oops, x replaces with 1. Combine some like terms. No matter how we arrange the equation and clean it up, we're still left with two unknown constants. Okay, we still don't know what a's and b's are, but we've gone as far as we can go, and now we need help from a different equation. So differentiable means a smooth curve. So what we want is we want the two graphs to share the same slope. At their meeting point, at their potential meeting point, at x equals 1. So if we want the two graphs to share the same slope, how do we find, what do you think we need to find if we want to find information about slope? Derivative, yeah, derivative. So let's find f prime. Let's find the f prime piecewise function. And that's why I gave us that you picked up the other worksheet, because I realized that we need practice dealing with constants. It kind of throws us off. Sometimes we think of constants as variables, and then it prevents us from being able to find the derivative correctly. So imagine ax plus 3 is just like 3x plus 4, right? The a is just some unknown number that's in front of x. So what do you think the derivative of ax plus 3 would be? Just a, yeah. Imagine 3x, right? 3x will become 3, 5x will become 5, ax becomes a. Good. What do you think the derivative for 3x squared plus x plus b would be? Okay. 6x plus 1. What happens to the b? Drops off. Yeah, it's not 1, it is 0. So just 6x plus 1. Okay. We're going to get some more practice with derivative involving constants, but a lot of times we think of a's and b's as variables because it looks like a variable, but they're telling us that a's and b's are constants. So we can set the derivatives equal to each other because we want these two slopes to agree at x equals 1. So a is equal to 6x plus 1, I'm going to replace x with 1 because we want them to agree at the same y value. So, or sorry, we want them to share the same slope at x equals 1. Now this one is nice. We can just go ahead and solve for a, right? A equals what? 7. And then if I have a equals 7, I can turn around and figure out my other unknown constant. So with these problems, the strategy is the same. You're going to set the equations equal to each other, and then replace the x value with wherever the center of the problem is. They always have to tell you where the breaking point is potentially. And then you're going to set the derivatives equal to each other, and then use both equations to help you solve for your missing constants. Okay, so now that we've seen and we've done one together, you guys want to try one on your own to see how, to see if this makes sense to you? Okay, so follow the steps, see how far you can get. The key is on the next page, but try first before you look at the key. Okay, so the continuous side of things, we know we want the two piecewise to meet at x equals -1. So we can set the equations equal to each other, replace every x with -1, and I get it all the way down to a equals 2b plus 1, but we're still unresolved. We still don't know what a's and b's are, but we can move on to our second equation that we can create. They're also telling us is the graph is differentiable, that the graph is going to have to connect in a way where the steepness is going to have to be shared so that they can be a smooth transition from one graph to the next, which means we can set their derivatives equal to each other. And we got to make sure we can find a derivative though. 2x squared becomes 4x, 2x becomes 2, a is a constant, a drops off to 0. Negative 2bx, that's just going to be some coefficient in front of x. Negative 2bx becomes negative 2b, and then 1 goes to 0. set them equal to each other, replace x with -1, and I'm able to solve for b. B is equal to 1, and if b is equal to 1, I can use my first equation to help me solve for a. 2 plus 1 is 3, so a equals 3. The trouble that I see students experience from previous years is finding the derivatives and involving constants and not quite finding the derivative correctly. So even though the steps are correct, the derivative threw them off, and that threw off their answers. Okay, let's try one more of these. This is going to be on page 29, number 5. Next page, page 29, number 5. Notice that this only says differentiable everywhere. The reason why they don't say continuous is because if it's a smooth curve, then it's guaranteed that it's also continuous. So a lot of times they can say continuous and differentiable, but that's kind of like saying, that's kind of like saying repeated information, right? So they just say differentiable, but we have to understand, okay, there's a continuous portion, there's also a differentiable portion. We want to apply the same process. Set the equations equal, set the derivatives equal, and then use both equations to help you solve for A and solve for B. We set the equations equal to each other. Ax cubed equals x squared plus b. Replace every x with 3. See how far we can get. We can get all the way down to 6 equals 9, or 27a equals 9 plus b. And then we move on to our derivative side of things. We know that the curve also must share the same slope at 3. So derivative ax cubed becomes 3ax squared. X squared plus b becomes 2x. Replace x with 3. We can solve for a equals 2/9, and if a is 2/9, go back to the first equation and solve for b. Any questions? Okay, so I want to stay on this for a little bit in case anyone else is working, but go ahead and see if you can try finding derivatives on this sheet that they just picked up this morning. So the constants that tend to show up on AP exams are A, B, C, and K. I mean, there may be other constants, but they have to tell you that's a constant. So you're going to treat A, B, C, and K like as if they were a number, right? Like a 5 or 6 or 8. And College Board, they love to do this. They love to insert these random constants into the equation and see if students can still find the correct derivative. I'll do the first two with you and see if you guys can. We may not have time to do all of them, but I just want to at least have you guys think about, that we want to treat these unknown, that these constants, that these ABCs as constants. Okay, so 3ax squared plus bx plus 5c. Let's find the derivative for this function here. And 3ax squared becomes what? 6ax. Bx becomes b, and 5c becomes 0, right? We don't say 5c becomes 5. Remember, c is not a variable. 5c is a constant. Number 2, f of x equals 3 pi, parentheses a plus b to the 4th. You have to go through chain rule. Actually, do we see any variables here? No. So this is just one big constant, right? So the derivative is just what? Just 0. Number 3, f of x equals 3x to the 4th over 5b. There's no need for a quotient rule because there's only a variable up top. So what if we just hold all the numbers out as coefficients, and then the only thing left to do is power rule? So what if we rewrote this as 3 over 5b times x to the 4th? Then it just feels like, okay, that's just some number in front of x to the 4th. Once I find the derivative, that constant is just going to tag along or as part of my derivative. Right. Number 4, is there a variable in number 4? Yes, right. So this is definitely a function within a function. We have to go through what? To find the derivative. Chain rule. Yeah. So identify your outside, identify your inside, and then take turns with each derivative. Outside's derivative is 12 parentheses to the 3rd. Keep the inside intact. Then we move on to the inside portion. 5x plus b just becomes 5. 12 times 5 is 60. I'm just cleaning that up slightly, but there's our derivative. Okay, number 5, we also have to use what? You guys see that there's chain rule required for number 5? But we want to rewrite it, right? Let's get the parentheses to show up. We can rewrite that radical as what? Parentheses raised to the 1 over 7, right? So do outside's portion first. That's power rule. Inside's portion, you can go through power rule, but just watch out for those constants. outside's derivative, 1/7 parentheses to the -6/7. Inside's derivative, 5ax becomes 5a, the 12k just goes away. And then we just clean this up, try to get it down to one fraction. Okay, try number 6. Actually, try 6, 7, and 8. The only thing you need for all these are just power rule. And then I'll walk through 9 and 10 since those are implicit problems. Yeah, so I want us to be comfortable with those constants. So when we see it on the AP exam, that we're not thrown off, right? That we're just practicing recognizing them as constants and treating them accordingly. And number 6 is just some large constant in front of my variable to the first power. So it's like 5x, right? 5x derivative is 5. So a constant times x will just become that constant. Seven, you may be tempted to want to go through quotient rule, which you could, but all that mess is just a constant, right? So if we just bring the variable up to the top, then we can just go through power rule. If you're done with 7 and 8, go ahead and try number 9. Number 9, there's implicit involved because you see y's in multiple places, and it's kind of mixed into the equation. Okay, so number 9, implicit involved here. So 3by becomes 3b dy dx. And then y becomes dy dx. I really think that if it's just a y by itself, I really encourage you guys to put a 1 in front. I'll show you why in a second. 5x becomes 5. And then the 12a goes to 0. Okay, we're going to collect the dy dx terms on the same side. factor out the dy dx. We're left with 3b minus 1 in the parentheses, and then divide the 3b minus 1 over, and then my dy dx is just negative 5 over 3b minus 1. Okay, something subtle here that I want to point out is, why am I encouraging you to put a 1 here, even though it's not completely necessary? This is what I've seen. If you don't put a 1 there, I see some students do this where they factor out the dy dx and they say, well, I have 3b and I took everything out, so there's nothing left. And their answer ends up being negative 5 over 3b. And having that 1 here is a reminder that when you factor the dy dx out, there's still a leftover term there. That's meanwhile, if you don't see that 1 there, you may be thinking that you got everything that you need, and that may throw you off. So that's the only reason that I encourage you to put a 1. It's not wrong if you don't. It's just it's easier to factor correctly if that 1 is sitting there, as a reminder that there's still something left over when you factor a dy dx out. Okay, number 10, implicit. Again, we have multiple y's. Is there something else that we have to be aware of when we find the derivative? Has to do with this 2axy. Anything stand out to you? What process is required? Product rule. There are 2 variables here that are being multiplied. So we got to go through product rule here. I'll treat the 2ax as one thing, and I'll treat the y as the other. So f prime g plus fg prime. Two ax becomes 2a. Y is my g. Back to f, 2ax. And g prime is 1 dy dx, or dy dx. Y is 1 dy dx. What about the abk and the 12b? This becomes what? Just 0, yeah. Okay, so we'll collect our dy dx terms on the same side, factor the dy dx out, and then we'll subtract the 2ay over to the other side as well. Hey, let's go to page 30. Let's do a particle motion problem. Page 30 at the top of the page. Go ahead and try number 6. You guys can cross off 7 and 8. I'm not going to put general definition on the test. So top of page 30, go ahead and try those. Let's see how far we can get. So before we can figure out when the particle is moving left, you first have to find the velocity function, set velocity equal to 0, create your velocity sign line. So all those things have to occur. You got to get that sign line all filled out before you know the interval where it's moving left. And the key is on page 32 if you want to check your progress. Okay. When is the acceleration, sorry, when is the velocity increasing? For part B, we know velocity is the slope of, we know acceleration is the slope of velocity. Increasing is basically asking about the slope of velocity. So we'll create our sign line for acceleration and see when is acceleration going to be positive. Basically, when is the slope of velocity going to be positive? Plug 1/2 into acceleration, I'm going to get negative. Plug 2 into acceleration, I'm going to get positive. So I know that my acceleration will be positive on the interval from 1 to infinity. This is when my velocity is going to be experiencing a positive slope. And find when the speed is decreasing. This is when velocity and acceleration have what? Different signs. Yeah. So if I can just stack my two sign lines above each other and see where they're going to have opposite signs, maybe I can stack them a little better here. So what intervals do you see them sharing different or having opposite signs? Yeah, this interval here, right? They start off sharing the same signs, but then after one, between 1 and 2, velocity is negative, but acceleration is positive. And after 2, they go back to sharing the same signs. So between 1 and 2. Where's the particle located when the velocity is 0? So we know velocity is 0 at 0 and 2, so we can just plug that into the position function. A little bit tedious to plug in, so this you can use your calculator. But I'll just give us the answer here: -1 and -11 volts. Because in this case, for this problem, the particle is not moving at 0. Because when we set v of t equal to 0, 0 ended up being a place where it's not only an endpoint, but it's also a place where the object is not moving. So we don't include 0 because there's no movement at 0. That wasn't the case on the quiz, because on the quiz, when we set velocity equals 0, we didn't find t equals 0. So that wasn't a location where the object wasn't moving. But in this case, now if this did not show up, if velocity, when we set v equals 0, if 0 doesn't show up, then yes, then we would include 0. Okay, displacement. Displacement is just final position minus initial position. So it's s sub 3 minus s sub 0. Yep. S sub 3 is -1. Plug into your position function. S sub 0 is also -1. So my displacement is 0. So that means between 0 and 3 seconds, he's going to be at the same location. And then finally, distance. We'll do some more practice with this tomorrow, but distance, you're going to use the same location as displacement. But then there may be one more or two more that you have to use depending on your velocity sign line. So between 0 and 3, does the object change direction? At what time? T equals what? 2. So we have to include that as well. So you got to include the endpoints in any places where there's a change in direction. And then we just find those locations. This is a little messy because you got that fraction here, but essentially you're just walking between the two locations and finding the distance between them. So between -1 and -11/3, I just basically subtract them and take the positive value. I'm going to walk 8/3 steps. And if I subtract these two, it's also another 8/3. So that's going to total to be 16/3. And everything is positive because you're always doing positive steps, even if you're moving left or moving right. Tomorrow we'll do some more review, maybe do some more implicit differentiation, more horizontal and vertical tangent. If you look really quick on page 45, this is what your test topics will look like. It'll be 3 pages, and there's going to be extended implicit differentiation problem. We'll do one of those tomorrow. There'll be a graph problem where You gotta do either product quotient or chain rule and then pull your slope or y values from the graph. We did that yesterday. Derivative involving power, product, quotient, chain, implicit, maybe a mixture of them. Particle motion, we just did that now. And then a differentiable piecewise function that we did at the beginning of class where you gotta solve for A and B. All right, come get your phones.